أنعمت عليهم غير المغضوب عليهم ولا الضالين آمين. بسم الله الرحمن الرحيم. الحمد لله رب العالمين، والصلاة والسلام على أشرف الأنبياء والمرسلين سيدنا محمد وعلى آله وصحبه أجمعين. اللهم إنا نستحفظك ونستودعك ديننا وإيماننا وأنفسنا وأهلنا وأولادنا وكل شيء أعطيتنا. اللهم جملنا بالصحة والعافية والسلامة والسعادة، وحققنا بالتقوى والاستقامة، وأعذنا من موجبات الندامة في الحال والمآل، إنك سميع الدعاء. اللهم مجلسنا هذا محاطا بالخيرات والمسرات والأنوار والبركات، ويقضي لنا بها جميع الحاجات، خصوصا بهذا المجلس IEEE Workshop on Geoscience and Remote Sensing 2020 برحمتك يا أرحم الراحمين. اللهم اجعل بلدنا ماليزيا آمنا مطمئنا سخاء رخاء دار عدل وإيمان وأمن وأمان وسائر بلاد المسلمين. اللهم إنا نعوذ بك من البرص والجنون والجذام ومن سيء الأسقام برحمتك يا أرحم الراحمين. ربنا آتنا في الدنيا حسنة وفي الآخرة حسنة وقنا عذاب النار، وصلى الله على سيدنا محمد وعلى آله وصحبه وسلم، والحمد لله رب العالمين.
Thank you to Mr. Ahmad for the dua recitation. Without further ado, I would like to invite Dr. Zafri Baharuddin, Local Organizing Committee Chair, to deliver his welcoming speech. Please be welcome.
Assalamualaikum warahmatullahi wabarakatuh. Very good morning to one and all present here. Thank you for joining us today on the IWGRS 2020. This is the first conference in the history of our chapter which is completely conducted on a digital platform due to the ongoing pandemic. The IEEE Geoscience and Remote Sensing Society, GRSS, is a professional society dealing with the theory, concepts, and techniques of science and engineering as applied to the remote sensing of the Earth, oceans, atmosphere, and space, as well as the processing, interpretation, and dissemination of this information. The IEEE GRSS Malaysia chapter welcomes you to join us in our shared interest in the field of geoscience and remote sensing. I myself have made many friends from the IEEE, many of which are part of this workshop. I would like to thank all the participants and my tireless organizing team consisting of GRSS members from the Malaysian Space Agency, MISA, the Institute of Geospatial and Remote Sensing Malaysia, IGRSM, the Science and Technology Research Institute for Defence, STRIDE, University Technology Malaysia, University Technology Mara, University Tunku Abdul Rahman, Multimedia University, and University Tenaga Nasional. Special thanks to University Tunku Abdul Rahman for providing this Zoom event, and the Energy Sphere in University Tenaga Nasional for managing our event today. Your efforts make this workshop possible. What I enjoy about workshops and conferences is the interaction and knowledge sharing between like-minded people from all around the world. Even more so for remote sensing, as it's such a multidisciplinary area. I request all the delegates and participants to take part in all the sessions that we have arranged for you today. I am now sending a link to the program book, which you can use to, where is it? Here's the link to the program book. Please use it to manage your time. We have a bit of time in during the lunch break. Once again, I hope that you all take part in all the sessions. Once again, thank you to all participants for being here today. I wish everyone a successful and fruitful workshop. Thank you. Back to you, Mira.
Thank you, Dr. Zafri, for your welcoming address. So next, I would like to invite Prof. IR Dr. Yu Hon Tat, IEEE-GRSS Malaysia Chair, to deliver his opening address. Please be welcome.
Thank you to the MC, Tuan Haji Azli Kamil Nafial, Director General of Malaysian Space Agency, and also our keynote speaker, Professor Dr. Daya Segar from Indian Statistical Institute, Bangalore Center, who is also our keynote speaker today, Dr. Zafri Baharuddin, the chairperson of the organizing committee for this IWGRS, the committee members of the IEEE-GRSS Malaysia chapter, participants, presenters, ladies and gentlemen, very good morning to every one of you. It gives me great pleasure to welcome and thank all the keynote speakers and participants to the IEEE workshop on geoscience and remote sensing 2020. This is our annual workshop with an aim to provide an intellectual platform for the IEEE Geoscience and Remote Sensing members, as well as other participants and students to share knowledge and experience on recent developments and advancement in geoscience and remote sensing technologies. In this era of rapid technological development, it is important to bring out the awareness of sustainable development, and remote sensing is a key technology in providing such capability for monitoring Earth, natural terrain, and also resources at large scale. This year, the theme of IWGRS 2020 is remote sensing for health and the environment, which is timely when the world is actually facing the challenges of COVID-19. Due to that, this workshop is held online for the first time, and I hope that this new approach will let us explore and develop new way of sharing and communications of latest research outcome and knowledge. For your information, I think for those officers who have attended IGAS 2020, it was actually also held everything online. So I think next year is IGAS 2021 is supposed to be held in Brussels, Belgium. Okay, but we still waiting for the final design of the program in terms of the mode of the conference. I think that they are trying to plan for something hybrid if travel by that time is actually safe to do so. And for information, I think IGAS 2022 actually will be actually organized by Malaysia, will be in Kuala Lumpur. Hopefully by that time, we have actually overcome this COVID-19 pandemic and everybody is free to travel. So again, I think this is, we hope that everything will be improved, and hopefully in future, IGAS 2022 will be actually held in Kuala Lumpur in physical mode and also maybe in hybrid mode as well. I would like to take this opportunity to also thank the organizing committee members for IWGRS 2020, as well as all organizing universities and organization of this workshop for your dedicated work and also strong support. This time, because of having this IWGRS online, and we have actually record number of participants as well, over 200 and from many countries and economies. So I would like to actually also take this opportunity actually to thank all the keynote speakers, the presenters, and also invited speakers, and also the all the participants for this event. Finally, I would like to wish you all the best for participating in this workshop and to stay safe and stay healthy. Thank you. Terima kasih.
Thank you, Prof. IR Dr. Yu Hontat, for your welcoming address. Okay, next, it's now time for the keynotes. To introduce our honorable keynote speaker, I would like to invite Prof. IR Dr. Koo Voon Chet from Multimedia University to chair the keynote session. Please be welcome. I'm sorry, Prof. IR Dr. Koo, we couldn't hear your voice.
Hello.
Yes, we can hear you.
Yeah, yes, it's okay now.
Sorry, Prof, it's gone.
Sorry again, but we didn't hear your voice.
Sorry, can you hear me now?
Yes,
Yeah,
yes.
it's clear now.
Okay, sorry about that one. Once again, good morning and welcome all to this IWGRS 2020. Today, we are very honored to have two very special keynote speakers. First, allow me to introduce our first speaker, Tuan Haji Asli Kamil bin Haji Nabil. KB Asli, I think everybody know him. He need no further introduction, but let me just brief you on his background. So KB Asli was born in Pasir Panjang, Kinjang, Selangor in 1969. He started his professional career in the private sector as a senior geologist in 1993, and he joined government sector as research officer at the Malaysian Remote Sensing Agency, formerly known as MAKERS, in 1994. And during his career as research officer, he gained formal knowledge through certified training in remote sensing in Australia, UK, and the Netherlands. At MRSA, he confers his knowledge and experience in spatial data analysis and modeling activities, including satellite image processing, to help Malaysia exploring the advancement of remote sensing technology for national development, security, and people well-being. He was also very active involved in ASEAN Subcommittee of Space and Technology Application. And also he has been appointed as one of the executive committee of ASEAN Regional Training Center for Space and Application based in Thailand. And after 10 years of invaluable contribution in R&D at local and international level, he was promoted as Special Officer at MRSA Director's Office in year 2004. And he is also an active member in the Institution of Geospatial and Remote Sensing Malaysia, IGRSM. With vast experience in R&D and technical management, he was then appointed to lead the corporate and strategic section in MRSA for 4 years, and later promoted as the Deputy Director General Technical Service MRSA in the year of 2011. Since 2015, he was appointed as Director General of MRSA with a task of spearheading the development and operationalization of remote sensing and related technology in Malaysia. With the merger of the Malaysia Remote Sensing Agency and the National Space Agency in 2019, he has been appointed as the Director General of the Malaysian Space Agency, or MISA, today. So with that, without further ado, I would like to invite our KB Asli to deliver his keynote speech. KB Asli, the floor is yours.
Bismillahirrahmanirrahim. Thank you, Professor Dr. Koo Voon Chet, Chairman, Professor Engineer Dr. Lee Hon Tat, and all the panelists, participants online this morning. Actually, it's a great pleasure for me to be part of IWGRS 2020. So maybe let me share my presentation. Can all of you see the slide? Okay.
Yes.
So okay. So I will talk about within this specific time. I try to share the activity in our country, in Malaysia, particularly on the development of space science, in particular the remote sensing program, and what was in our planning for the next 10 years. Okay, as we recall that in our country, space sector actually merely focus into three sectors, namely is remote sensing, communication and navigation. Even though there is many more aspect of remote sensing in our country, but these three cluster is become dominant in our development and also some operationalization, either in the first layer or even second layer. First layer definitely is championed by the government and some international relation of the development of the technology. So I would say that within these three cluster, communication is more towards to the commercialization or contribute to the economy. But remote sensing purely on the how we can develop this technology and adapt to the community at large. So as I said just now, even though there's three cluster, but public at large normally will be familiar with this cluster, either Earth observation or remote sensing, and the communication purely for our TVs, telcos, and all that. And also GPS, global positioning and navigation system, which we are now, I think, is a must to everybody in our country, and definitely the meteorology, being a tropical country, this scenario is quite important to us. Anyway, since the development of the space technology in Malaysia, if I can recall, it was started 1988. So at that time, we already planned how this space technology can evolve in our country to ensure that this technology can create a huge impact to our development, also some economy. So we start from the user segment. At that particular time, is quite difficult to us to introduce the new technology to the public at large. That's why we are focusing into the how this technology can facilitate them in daily life and also some operationalization. So the downstream part is quite interesting at that particular time until 10 years of period. Then there is a demand increase to utilize this technology, and then we set up the ground segment. It was to actually to facilitate the data information. They need the real-time data to process and to utilize that. But after, I would say that after 20 years, we are still lacking in space segment. So this is upstream activity that need to be there to support the continuation of the user and also ground segment in our country. So it's some sharing info to the panelists and also the audience online today, this morning. So as you can see that we are start in 1988, more on the downstream activity and certain part of the upstream activity. We do experience some R&D satellite during Tiong-Sat exercise and also some Razak-Sat exercise. We do have some experience with the astronaut and to ensure that this momentum can be increased in terms of the development of the space technology in our country. So the major thing is happened in 2017, where the National Space Policy is formed, and agreed by the government to implement towards 10 years implementation period until 2020. I think this is the major turning point to us in our country to ensure that this technology can evolve further to benefit in terms of our economic and also some people on the ground. So I could say that since 2017, the development of the national space policy, the merger between remote sensing and National Space Agency is one of the key criteria in Trust 1 of the policy. So it's meant to strengthen the management of the space activity in our country. So I think it's a good start to us here in our country. So in terms of the development of the technology, I would say that the remote sensing technology services and also the R&D is among the major activity that's already in place and can be strengthened further for the next 10 years. As you can see that the remote sensing start with the military exercise. I could say for the last 20 years in Malaysia. But now, since the technology is more advanced, it can be utilized in many field of activities. So there is a huge potential of the remote sensing activity in Malaysia for the next 10 years. I could say that among the challenges we are facing to ensure that remote sensing services or even the activity can be enlarged in our country is the adoption of the technology itself for the public at large. So other than that, I think since the advancement of the technology also gives us some challenges to ensure that this technology can be benefited in all parties. Okay, how can remote sensing or even now in MISA serve the country in terms of the utilization of the space activity and space technology? To date, I think this system has been developed way back 10 years ago. So it called it IWGRS apps. It was a specific services which is include the development and also operationalization of the application which developed together with the end user. So it is quite interesting because in early stage we are focusing into the government and government department and agencies to ensure that the services can be upgraded into the efficient services of the government. So to date we have at least 65 government department utilizing this system in one-to-one operationalization. So it was a 24/7 based system and to some extent it is also based on the requirement from the user agency, and it was dedicated to some department. So I could say that the increasing of the demand for this optimizing of the system is very demanding to today. And then to some extent we need to explore a new application to solve many problems from the government department specifically. So it's not only about the military, but it's about the environmental, about the natural resources, and in many of the applications that arise facing some problem to be in optimal operationalization of our country. So I could say that today we have at least 40 systems based on the remote sensing. It is, as I said, is operational 24/7, and to some application is based on the requirement from the user itself. So this system since 2012 is developed. We developed at least 5 new systems each year So that's why we have a target until 2030. Is many more applications that can be established to serve the end user in our country. So even though we are just servicing the government department, another target is to actually to ensure that the government we able to save the government operational costs. As you can see on the slide, up to date, we managed to save the government money until to 49.8 million. So it's quite interesting to the government to ensure that our services and operational can be upgraded into the better one. Just to share some example application that we already developed and operationalized throughout the country. This is together with the Jabatan Pertanian, Agriculture Department, to manage 12 rice field in the country. So using this remote sensing or even space technology, you can see that I'm sorry, some of the point is in Malay, but I can explain that. So it reduced the monitoring time until 57%, and the most important thing is the subsidiary. So it reduced the government burden to ensure that only the targeted subsidy can be disbursed. So this is the most important application, and this application is continuously operate until today. And to some extent, we are trying to expand now to the area that we are didn't cover previously. So another application that developed together with the fishery department to ensure that our fishermen can have a good impact with this space technology. So utilizing the information from remote sensing, we can help at least 50,000 fishermen throughout the country. To some extent, with the record since 2010, we can help the government to save at least 354 million in terms of the import of the fishing from other countries. So this is the one of the benefit and impact that space technology contribute to our country until today. Another application that I can share, the development of the underground water exploration on the hard rock terrain, together with mineral and GMG department, geology and mineral department, and some chemistry and some parties from Ministry of Health. We try to explore the best area to do underground water exploration using the information gathered from the space technology, particularly in remote sensing. So today we have at least 10 locations. In specialty, the location is actually very remote area and in hilly terrain area. So we managed to explore this potential and to some extent reduce the cost to develop the underground water exploration and facility developed together to serve the community. So thanks to the technology, and you can see that so how many people that benefited from this activity, and they have a free water every day. So another aspect of application that has been developed is on the forest fire monitoring system. I think within the Southeast Asia, we are the country that always facing the similar problem every year. So with this technology, we can actually have the many parties, either is enforcement or planning, or even we have some evidence of the activity throughout the Southeast Asia. So this is the important application we need to have, and thanks for the technology, and it benefited many parties, particularly on the enforcement parties. So for the natural resources, you can see that even though it's some words in Malay, but it is about the forest monitoring system. So we work together closely with the forestry department to ensure our natural resources, particularly on the forest reserve, can be monitored regularly, and to some extent to reduce the time and cost of the monitoring throughout the country. Many have heard about the dengue previously. You can see that this is also part of and parcel among the 40 applications that were developed since 2011, and SB continuously operate together with the Ministry of Health to ensure that the management of dengue pandemic can be tackled accordingly and more systematically. So part of the entity under this system, IDengue, is the communication with the community directly. So it will be more useful to not only to the Ministry of Health but the public at large. So together with other departments such as the community, so we are also now enlarge the functionality of the system to monitor all the community in our country. So as I said just now, way forward, space technology, particularly on the remote sensing itself, we plan to have to roll out to at least 110 government agency towards 10 years implementation, and we can have at least 90 system application based remote sensing, or even satellite or even space technology in the coming future. So as you can see that the separation of the demand from the user itself. You can see the natural resource management environment is among the top. So to date we have 14, but I'm sure that in the next few years to come, it will be increase the number of the demand of the application. Okay, we're back to the functionality of the Malaysian Space Agency. MISA is among the new agency under the Ministry of Science, Technology and Innovation. With regard to the merging of MRSA and also Agensi Angkasa Negara. So the function actually, the main function of MISA is definitely to spearheading the implementation of the National Space Policy 2030. This is the main role of MISA to ensure that the implementation can be smoothly run towards 10 years, towards 2030. At the same time, we are also encouraging the research and development in space sector. Previously, we are talking about only the downstream, but now we are venturing into the new upstream activity to ensure that we can cover the comprehensive ecosystem of the space technology in our country. Another function that we are focusing is also the empowering the national capability in space sector. So this include every sector, including private, government, educational, and also NGOs. And we also to ensure that we can strengthen the international cooperation in the field of space within the next 10 years. So just some briefly of the how MISA is formed since 2019, but now is I could say 1 year old age of the MISA, but we have a good planning for to implement towards next 10 years. Okay, since the merging of the Malaysian Remote Sensing and National Space Agency, now we have a complete ecosystem from the management, technical, and services. So we have a 4-branch HQ in Kuala Lumpur, ground segment in Temerloh, and the technology development and manufacturing in Banting, and also we need to enlarge the functionality of National Observatory in Langkawi. This is purely on the space science activity for R&D. So become a new and important entity to MISA to evolve to the next level of the achievement. So this I said just now, our observatory national in Langkawi is a good infrastructure to be applied in terms of the R&D, particularly in the space science. So as I mentioned just now, another important thrust under the national space policy is to ensure that our activity is in line with the international policy. So this is the part and parcel of activity is currently we are doing, particularly to ensure that we are also governed in the international outer space treaties. So as you can see, for the last 2 weeks, our minister has been reading the first reading of the Space Act in the Parliament. So this is a part and parcel in Trust 1 to strengthen the government agenda in terms of space establishment in our country. So Space Act is one of the activity in the Trust 1 in National Space Policy. So one of the bigger program that we are planning for the next 10 years is particularly to ensure the implementation of the national space policy can be rolled smoothly. We introduced the Malaysian Space Exploration 2030. It comprises 4 clusters. As you can see that it's a good colorful here diagram. You can see the user segment is in yellow. The cluster we have already in certain level of achievement, so we can enlarge throughout the next 10 years. Another segment is a ground segment. Also, we already reached to some level, so we would like to continue the development of this ground segment. The space segment is, as I said just now, there is a few more activity need to be in place to ensure that we can have a good ecosystem for the upstream activity, particularly for local industry. So the final one is the knowledge creation. This is where the joint basic research, talent development, we can have with our academia, university, or even the industry to ensure that the sustainable of local capacity in our country, particularly on the space space-related technology, can be assured for the next 10 years. So all this activity in 4 clusters governed by the National Space Policy and also the Space Act. So I think industry and also the NGO, including the academia, can play a better role within this Malaysian Space Exploration 2030. So this is part and parcel. If I can share some of the strategic activities be in place or even being planned for the next 2021 and onwards. As you can see that on the left hand side is more towards to the strengthening the governance, and then followed by the focus on the national space technology infrastructure, we need to have a few entity and activities, major activity that we can chart on to ensure that the space technology development can be flourish in our country. So spreading space development science, this is more on R&D, towards the R&D space science, including the how we can enrich the we call it research industry, scientific exchange, and some space science research. The following is contributing to the national economy and societal well-being. This is the major agenda of the country right now. We are facing the pandemic throughout this year, and then we need to see that this space activity can contribute to our economic development as a new economic pillar to the country. Hopefully by within these 10 years. So definitely the final one is to increase the strengthen and cooperation in the national network, international network. So we also have some UPSAF, UN, USA, SCAP, all those things. We need to enrich this activity. So as you can see that just explaining a little bit in the diagram manner. So we plan for the satellite development program towards 2030, 1 or 2 satellite. And then we need to optimize the AIT lab capability now. It's already in place in Banting. We also had the Space Act just now. I explained on the first reading in the Parliament. And next year onwards, we are embarking into the space industry roadmap. So to ensure that the ecosystem, space ecosystem in Malaysia can be sustained with the good support in terms of the development and also the operationalization. So this is part and parcel where space industry can contribute, or even in line with the government approach currently to ensure we can also build up our economy for the next 10 years. You can see that how relevant space industry in Malaysian digital economy, Penjana, also the shared purpose vision 2020. I could say the space technology at least can be as an enabler, at least 3 of the enabler in shared purpose vision 2020. One is the sustainability, enlightenment space society, and also the effective institutional delivery plus government integrity. So most of the enabler in shared purpose vision 2020 is can be contributed from the space activity and also initiative. Okay, just some what we call it the scenario in our country. We do have some industry also start up in various cluster, either in space-based manufacturing, ground-based, or space-enabled product and service provider. So this is to me is a starting point to ensure that all this ecosystem can be enlarged for the next 10 years to generate or growth our economy based on space technology. Okay, based on the Space Act previously, the last 2 weeks is tabling in the Parliament. So this is part and parcel our aim, where we can facilitate the growth of the economy through at least 5 pillars. You can see that we need to have international standard on our manufacturing services and also data. We need to have at least 100 subject matter experts in various aspects and background, either it's a mechanical, structural engineering, or space environment, or all those things. So this is the part and parcel activity can be facilitated through the good systematic and ecosystem policy and also the Space Act. So definitely government looking into how we can generate a new job to our scientists for the next 10 years. This is also part and parcel. We aim for the next 10 years under this Malaysian Space Exploration 2030. So we are not forgetting our partners internationally. So definitely this is part and parcel where we can have the knowledge creation linked with the international entity. Now we are establishing the huge potential collaboration internationally. So with the major player in terms of the space industry or even in the space R&D. Okay, I think this is my last slide. So this is our aim for the next 2030. So at least with this growth of space industry or space science, we can contribute at least 0.3% or equal to 3.2 billion to our GDP for the next 2030, 10 years implementation period, and up to 5,000 new jobs for our scientists, and 40 million a year in terms of the data commercialization. So if the planning can be achieved, then easily we can be within the top 3 in the Southeast Asia in terms of the space technology research and development. So definitely we need to ensure that our self-reliance in this industry or this technology can be achieved at least 60% by 2030. I think that's the information that I can share with all the audience this morning to ensure that space technology can be one of the major contributor in the country economy for the next 10 years. With that, thank you very much.
Thank you, KB Asli. Thanks for your very insightful and very informative talk. I think now I've also have a better understanding on the national policy and also Malaysia's space exploration 2030. We are all very excited to look forward to contribute to this segment. Due to the time constraint, I think I can only pick 1 or 2 questions. KB Asli, there's one question for you. Regarding the Malaysian Space Board Bill 2020, did MISA get any authority to enforce government or related party to make remote sensing technology for decision making or during enforcement such as illegal deforestation? Can MISA take action or something like that? Yeah.
Okay, thank you, Prof, for the question. So as I mentioned just now, the major role of MISA is to ensure the implementation of a national space policy 2030. So one of the key elements in terms of to ensure that the smooth implementation is to ensure that this technology can be adopted in any part of any activity in the country. So I put some example now. Now is state of Pahang is continuously utilize the remote sensing technology in many of their activity, including the monitoring, planning, and all these things. So to me, the enforcement can be part and parcel in terms of the implementation of the National Space Policy. So that's why we are introducing the National Space Act. National Space Act, part of the entity is to facilitate any parties to ensure that they can utilize, optimize the space technology in their operationalization and also their activities, daily activities. Thank you, Prof. Okay.
Thank you. Thanks, KB Asli, once again. I think due to the time constraint, I think I have to stop this section. So once again, let's everybody to show thanks to KB Asli. Okay. So next, I would like to move on to our next speaker, Professor B.S. Saga. So let me just briefly read out the biodata of Prof. Saga. Okay. Prof. Saga now is a full professor of the System Science and Informatics Unit, or short for SSIU, at the Indian Statistical Institute. Prof. received his master and PhD degree in geoengineering and remote sensing from the Faculty of Engineering, Atra University, India. And in earlier days, he works in the College of Engineering Adran University, and Central for Remote Imaging Sensing and Processing, the National University of Singapore, and also the Faculty of Engineering and Technology, Multimedia University, Malaysia. So Prof has made significant contribution to the field of geosciences with special emphasis on the development of spatial algorithm meant for geo-pattern retrieval, analysis, reasoning, modeling, and visualization by using concept of mathematical morphology and factor geometry. He has published over 85 papers in journal, and he has authored or co-authored 11 books and also special issues for journals. Particularly his recent books entitled Handbook of Mathematical Geosciences, published by Springer, has reached over 500,000 downloads from worldwide. He was also elected as the member of New York Academy of Sciences, a fellow of Royal Geographical Society, a senior member of IEEE Geoscience and Remote Sensing Society, and a fellow of the Indian Geophysical Union. He is also a member of the American Geophysical Union and a life member of the International Association for Mathematical Geosciences. And he has delivered numerous lectures, particularly just the recent one is a Frank Harary Endowment Lecture 2019 at International Conference on Discrete Mathematics. He was also awarded the Dr. Balakrishnan Memorial Awards of the Andhra Pradesh Academy of Sciences in 1995, the Krishnan Medal of the Indian Geophysical Union in 2002, and more. He is currently the founding chairman of the Bangalore section IEEE Geoscience and Remote Sensing chapter, and he is now the IEEE Geoscience and Remote Sensing Society Distinguished Lecturer for this year, 2020 up to 2022. Today, Prof. Saga is going to give us a special talk on mathematical morphology in geoscience, remote sensing, and geospatial data science. Prof. Saga, the floor is yours.
Thank you, Professor Koo. Can you hear me?
Yes, we can hear you.
Yes. Thank you, Professor Koo and Professor Yutat Hang, and then Tuan Haji Asli, and Chani Kate, Lim Senji, and Dinesh Sachamurthy, and all these people were my former colleagues. And it's a kind of nostalgic feeling. And my most productive years are from MMU, Multimedia University in Malaysia. And I spent about 7 years. And it's a great honor for me to be here, though it is a virtual workshop. And to see all of you, it's a great feeling. And first of all, let me congratulate the Malaysian Geoscience and Remote Sensing chapter to start this kind of activity. I was told that this is the first ever activity, and then subsequently it's a nice experience for all of you to work for the IWGRS 2022. And I believe that the Malaysia is the 6th country in the Asia Pacific region to get the bid successful for IWGRS. And so congratulations. And so we could all hear such a wonderful overview to talk by Tuan Hazli on Malaysian Space Science and Remote Sensing Program, A Way Forward. And it's indeed a very broad topic, and the knowing about activities of Malaysian Space Agency, it's always a great thrill. But the topic that I am going to cover is it's a very, very narrow topic. It's all about a small mathematical theory. It's on mathematical morphology. And many of my colleagues in Multimedia University, and we try to popularize it. And even after its birth, that was in mid 1960s, and it is still a small group, but I still feel that probably being mathematical morphologist, and we didn't do a great job to popularize it across the globe. But it has wonderful applications in both geosciences and remote sensing. And of late, people have been seeing its success in geographic information science. Many of the challenges that were handled by spatial geodata scientists can be handled with a single mathematical theory, that is mathematical morphology. And let me just share some of my slides, and these slides would actually highlight, it's like a kind of illustrative overview about how mathematical morphology could be used in various different applications. And but I'm not going into details of the mathematical aspects of mathematical morphology because of the time constraint. I always feel that giving a shorter talks is very, very difficult, and because to squeeze everything by not losing the coherence is always difficult. But as you could see that mathematical morphology, it is about studying the shapes of the surfaces. What is the mathematics that we have to study the surfaces? And the surfaces that I refer here is earth-terrestrial surface. And it is a core topic in geosciences, and it doesn't necessarily be just planet Earth. And of late, we could show a number of applications of mathematical morphology in studying the lunar surface. And because in our Chandrayaan-2, we had Chandrayaan-2 was a satellite which they launched to sense the lunar surface, and where we had the opportunity to see the lunar surface with 25 centimeters resolution as a digital elevation model form. And all these powerful, spatial statistical algorithms have a lot of role to play in studying the surfaces. And it is not just in geosciences, and when it comes to remote sensing, and of late people have been talking about morphological profiles, extended morphological profiles, and attribute profiles, and they are all coming from the field of mathematical morphology and spatial data sciences. And it has not necessarily on earth sciences or geosciences applications, and we have applications where all that we can represent the data in a spatial form. And so mathematical morphology is a fundamental theory with a very small theory, but it has a huge number of applications, and that you can see. As I mentioned, it is just an overview, and I'm always grateful to Geoscience and Remote Sensing Society, and which I have actually the chapter similar to Malaysian chapter, and I have founded that similar chapter in Bangalore section. And so very recently I have been elected as a IWGRS distinguished lecturer, and so in turn, and thank you so much for all of you to give me an opportunity to be part of this IEEE workshop on geoscience and remote sensing. And as this lecture, and I don't go in detail, but I could realize that to handle information retrieval, information analysis, information reasoning, information modeling and simulation, and visualization, and these are all the main ingredients to study any dynamical system. Whether you are talking about the behavior of sand dunes, or behavior of water bodies, or behavior of the earth terrestrial surface, I would see that earth terrestrial surface is like a kind of physical system. And of late, people have been talking a lot about cyber physical systems, and there exists a geo-cyber physical system. And what all that mathematics or the core data that we employ is ultimately to make a kind of prediction. Are we talking about a subsystem like a sand dune? What is its behavior? And then automatically we have to handle both spatial resolutions and temporal resolutions across the time and space, how a specific system is behaving. And most of our remote sensing and geoscience communities are handling perhaps like, just how to classify an image. What are the classification algorithms? What are the clustering algorithms that we employ? And then finally, we end up with a kind of nice map. And is that really the end of our academic research? No. Whatever the map that we see, that we map, and as long as it is very accurate, And we have to use those maps across time periods to make a model. And subsequently, such model should give us a kind of information, it's a behavioral information. And then that is how we can actually make the spatial policies. And so for all these ingredients, eventually to talk about the behavior of a specific dynamical system or a geodynamical system, is there a single mathematical field that can really handle that? And I would say that the mathematical morphology can handle many of those ingredients, right from retrieval, analysis, reasoning, modeling and simulation and visualization. And you would see some of those snapshots in the subsequent slides and the meaning of why mathematical morphology can handle many of these ingredients. And this is the slogan, very recently it was coined by Dr. Paul Rosen of Jet Propulsion Laboratories. And he has mentioned after seeing my tutorial for IWGRS 2020, it is about mathematical morphology is an area of geoscience that most people don't realize will literally change the way they look at Earth. And this morphological thinking is so important because we talk about the shapes, sizes and their distributions and the functions and their roughness and the roughness, the global roughness and directional roughness, all that. And if we can really explain this to the young audience, and I'm sure that they can take this field to the further heights, and then it has a lot of promise. And that is what I have realized by spending almost 30 years working on only on mathematical morphology applied to Earth's terrestrial surface. As I have already mentioned that these are the main ingredients, whatever that you have seen in when you are developing a spatiotemporal model. And so analysis, reasoning and retrieval, and finally to develop a dynamical system model to predict its behavior, and mathematical morphology is one of the better choices. And in one single slide, and if I miss, explaining the subsequent slides, you can glean a lot of things from one single slide. It is about a kind of, the synthetic terrestrial surface. And we have simulated this by calling this as a digital elevation model, which mimics the actual, the terrestrial surface elevation model. And from there, we can actually extract very, unique topological connectivity networks like ridge and valley connectivity networks. And when you look at your surveyed topographic maps and you see there are two prominent features there, blue lines. Blue lines are actually the channel networks, valley connectivity networks, and the brown lines are actually the elevation contours. And now actually we don't require, as long as we have very precise and accurate digital elevation model, and mapping of those things do not require any kind of, going for a survey to the physical site and map the features. And from sitting at, the remotely, you can actually map the features very accurately with a condition that the digital elevation models that we generate are very, very accurate. And they come with a lot of errors and uncertainties, but with the kind of, LiDAR kind of mechanisms and the DEMs that we are seeing are, very, very accurate of late. And those things, how to really exploit that particular data. And as such, if you look at digital elevation models, actually the whole world has spent billions of dollars in generating digital elevation models. We have shuttle radar topographic mission. I remember that we are using Topix GoTop digital elevation models for entire Malaysian territory. And I remember Dr. Taylor Etienne was using those DEMs, and her PhD thesis was on that particular DEM. And we have applied, successful algorithms from mathematical morphology. And these are the features, and I always like to specify these two great gentlemen, and Professor Georges Matheron and John Serra. These are the two people, co-founders of mathematical morphology. And then subsequently, and how to compute the roughness of a terrestrial surface. Is it for entire region, or you want to partition the entire region into watersheds and then you want to compute the roughness values? Because always roughness is linked to its behavioral aspects. And if the roughness is highly rough, and then we say that, so the corresponding entropy, the capacity to change that kind of terrestrial surface is to the greatest extent. The terrestrial surface is having a very smooth roughness, and then we say that it has reached to a kind of stability. And these things were earlier done through kind of morphometric studies, but of late, after digital elevation models have been emerged, and we require powerful spatial statistical and mathematical morphological algorithms to compute their roughness in terms of numbers. And then those numbers are not just necessarily for global index computation, and it is also for, in left to right, what is the roughness, from top to bottom, what is the roughness, and from diagonal directions, and what would be the roughness, and all those roughness values. And these particular DEMs are containing a lot of morphological, geometrical, and topological information. But with our naked eye, we cannot actually unravel all those morphological, geometrical, and topological features. And you have to take the help of mathematics. And one of those mathematical fields I would always recommend is mathematical morphology, followed by fractal geometry. These two have, the geometric essence to actually exploit these DEMs to unravel hidden morphological, geometrical, and topological features. And then subsequently, these are from remote sensing part, geoscience part, and remote sensing part, probably the mapping, and wonderful transformation called watershed transformation and power watershed transformations. And in a graph theory, by linking with graph theory, and recently my students have actually given power watershed transformations and power spectral clustering to map the features very, very accurately. And that comes from actually remote sensing part. And subsequently, if you look at all these features, and they all talk about geographic information science and geocomputing. And you have to have in a large database, when you have a large number of images, and you want to group them according to the similarity measures, and how morphology could be used. And I will show a couple of equations in subsequent slides. And then when you want to, you have a particular DEM of a particular period, and after 10 years, you have the DEM of the same region, and you want to find out what are the subtle morphological changes that have taken place and over a period of 10 years. And we require a kind of, powerful nonlinear interpolations. And we could actually propose nonlinear interpolations from the theory of mathematical morphology. That is particularly like, this is the source DEM, and this is the target DEM. And between source and target, you can create one median function. And between source and median function, you can create another median function. Between median and the target, you can create another median function. This would actually allow you to insert as many interpolated functions as possible in between the source and target. In such a way, you can actually make, sparse data into dense data. And we always, in remote sensing, there is a kind of repetitive coverage. Sometimes images are taken at the interval of 22 days, at the interval of 15 days, at the interval of 6 days. And can we really make predictions in between by following some kind of interpolations? And that is one aspect. The other geocomputational aspect is by taking a kind of, some very basic features, and can we actually generate a landscape which mimics the actual terrestrial landscape. And then this is about some kind of visualizations, cartogram based visualizations. And these visualizations, how do we handle? And so how morphology would help us. And then some kind of spatial optimizations are here. And I would quickly run through with the other slides. And I would skip many of those things. And as I mentioned, mathematical morphology, but I would show most of the slides are related to digital elevation models. And basics of morphology, I'll quickly show. And then morphology in geosciences, particularly to ridge valley network extraction and surficial computation, roughness computation, remote sensing for classification, how morphology was used in classification purpose. If you see in IWGRS, there is a group from University of Iceland headed by Jocelyn Chonsett, not Jocelyn Chonsett, sorry, John Bendixson. And this John Bendixson has formed a group, and then they started using mathematical morphology in a much different way how we have looked at morphology. And they started giving a kind of, morphological profiles. And morphological profiles are nothing but our granulometric analysis, which we actually use from mathematical morphology. but they have used as a powerful classification tool, and the results were the kind of classification that they do is almost 99% is accurate. And subsequently in geographical information science, how morphology could be used, morphing, and as I have shown, median computations and ranks for pairs of images and spatial reasoning and for such kind of studies. And then these are some of the digital elevation models, the source data that I would like to just show. And you can see this is our Chandrayaan-1 digital elevation model of the lunar surface, and which could only be in the orbit for only 9 months. After that, it was lost, and then so it was partially successful. But Chandrayaan-2 is a successful, where we can get very high resolution DEMs, that is 25 centimeters resolution DEM, and you can actually measure the shape of a rock on lunar surface. And subsequently, so in the next issue of Geoscience and Remote Sensing magazine, and I have written actually a kind of small opinion piece, about 4 pages opinion piece, that is about digital elevation models, an important source of data for geoscientists. And this data has been underutilized. Why? Because many people have been using only commercial softwares to use this data, to visualize this data, and to extract certain features from that data. But we have to develop a kind of curriculum at the probably at the undergraduate level, and digital elevation models and mathematics required to understand digital elevation model. The DEM as a black box, and there is a lot of information that we can retrieve from digital elevation model. How to handle that? It requires the knowledge in discrete mathematics, fuzzy set theory, mathematical morphology, wavelet theory, some kind of nonlinear dynamical things. That is what I have written. Probably I'll share once this is published. This is getting published in the next issue. And this is just a proof that I have shown it here as a snapshot. And in mathematical morphology, there are broad fields like binary mathematical morphology, grayscale morphology, graph mathematical morphology, adaptive mathematical morphology. Those who want to venture after knowing a bit of mathematical morphology, I would really recommend that they should get into graph mathematical morphology, which is showing a lot of promise. And because it saves time, very powerful. And I could see that somebody is talking about CUDA technology, using CUDA technology in the next paper. I think that is where, when we really realize about the importance of the time complexity, and we have to go for mathematical morphology in graph domains. And these are the 2 people and some equations, and I would skip, but I would share these slides with Professor Koo, and then he can share with the participants. And I would quickly run through that. It is about the whole mathematical morphology relies on 2 fundamental morphological operators: erosion to shrink and dilation to expand. The basis for these 2 morphological operations is actually Minkowski algebra, Minkowski sum and Minkowski subtraction. And then applying these operations in a recursive manner, what would happen? A shrunk version would be still shrunk if you perform erosion twice. And if you keep on performing that erosion, and the object would get vanished after a certain number of iterations. And similarly, if you keep on expanding a specific object and it occupies the whole universe, and so where to stop? And then you have to really think about some kind of geodesics. All that is some kind of advances in mathematical morphology. These 2 fundamental operations were extended to grayscales, because it is not just flat black and white objects that we are talking. We are talking about the functions. Like terrestrial surface is a function, a 2-dimensional or 3-dimensional function. How do you partition that? And partitioning actually comes from topological watersheds. But partitioning that the same terrestrial surface by a hydrologist is getting a hydrological watersheds. What is the basic difference between topological watershed and hydrological watersheds? So actually it requires a proper dialogue with hard thinking. What are the basic things, the different from the mathematician's point of view and from the geoscientist point of view? How nice it should have been if geoscientist knows about all these mathematical aspects. So the geoscientist doesn't need to rely on any other person or any other commercial software, and he or she can think morphologically and then generate wonderful algorithms to understand the terrestrial surface much better way. And these are the subsequently erosion followed by dilation is a kind of cascade operation. Dilation followed by erosion is another cascade operation. entire mathematical morphology is a completely nonlinear theory. And many people used to ask how superior it is when you compare with wavelet operations. And wavelet theory is entire transformations there in wavelets is linear transformations. But whereas in mathematical morphology, all transformations are nonlinear transformations, it has its own advantage over each other, of course. And then these are some of the slides that I would like to show. A original feature, a shrunk version, and a kind of opened version, a kind of closed version, cascade operations. And then you have a dilated version. And what would happen when you perform opening recursively? It keeps losing information. A function is losing information. What would happen if you keep on applying closing operation? It gains information. This losing and gaining information are to the nonlinear degrees. And the loss of information is not uniform. And we always work in mathematical morphology. There is data, and data has to be investigated with another kind of a probing rule. And this is typically two types of data. One data is investigating with another data. So what is that another data that you are using as a probing rule? That is very important. How to define and design that kind of probing rule. It's all in a number of challenges are there in mathematical morphology. And when it comes to the functions, and the X that I have used is a kind of a flat surface. And for this one is a kind of functions and the two-dimensional functions, and how these morphological operations were given. I'll quickly skip many of these slides, and if someone is interested how these morphological operations could be employed, and they can actually run through these slides. And then their representations in graph domain, and you now have for the last 10 years I've been seeing morphological erosion. What is its corresponding graph morphological notation, and graph morphological dilation, graph morphological opening, and they have wonderful advancements in graph mathematical morphology. And anybody is interested can get into. There are a number of review articles written by my excellent collaborator from University Paris, and Professor John Serra and Professor Najman. This is a long list of transformations we have employed in dealing with the channel so terrestrial surfaces, remote sensing. If somebody is interested, because I skipped many things, and actually mathematical morphology I can teach for a class in 20 hours. And those things you can actually look at some of these YouTube links I have kept here. And then if somebody is interested, can just attend it. And then we will look for an opportunity when I can come to Malaysia and I can give in-person lectures on these things. And it would be nice to, nurture young minds on those things. And very quickly, these are the things like a synthetic DEM and potential valley and ridge connectivity networks. And they are like green lines are valley connectivity networks, and blue lines are ridge connectivity networks. We have followed a simple skeletonization algorithms to extract these features. And then, so when you talk about a kind of roughness, and it is not just the superficial roughness, and you remove the skeleton from the terrestrial surface. What is the skeleton? A river network. And whatever is left over is actually called fat fractal. And if you can really pack that fat fractal with possible, regular GONs, and then you can derive some of the index values which are scale invariant but shape dependent. By changing the shape, here I have used octagonal shape. I can actually quantify this particular Apollonian space. It has a specific dimension called 1.36. And if I keep changing from octagon to circle and octagon to square, and I keep getting different number of numbers, and those numbers are scale invariant but shape dependent. So how we have used, and we have taken a kind of terrestrial surface, and from there we have removed the skeletal network, that is the river network, on the remainder, that is the fat fractal, and we followed morphological shape decomposition to quantify its shape and of course size. And so this is how we have actually packed. And I would skip those things. And then other very important technique in mathematical morphology is granulometric analysis, and how a surface looks. And when you are keep on applying erosion followed by dilation, and 2 times erosions followed by 2 times dilation, and n number of erosions followed by n number of dilations. A terrestrial surface traverses this kind of path, and it is losing information with the increasing number of openings, cycles of opening, whereas it is gaining information with increasing number of dual operation to opening is the closing. And that is what we have shown, and how the loss of information, gain of information is happening with cycles of increasing level of nonlinear transformations would help us to compute morphological entropy. From there we compute the roughness. And with that idea, and we could partition, this is actually the Cartosat DEM, which is an Indian satellite based digital elevation model. And then it is partitioned into 31 watersheds, and each watershed where we have computed the granulometric index, and global granulometric index based classification shows this particular classification. And whereas if you change, I set the probing rule, and probing rule from left to right and top to bottom, and these roughness values would really change. What is the high directional roughness for this particular watershed? This is in this direction, it is, the roughness is very high. And in whichever direction the roughness is very high and it is vulnerable for any kind of perturbation in that particular direction, it can break very easily. And the low directional roughness things. And these are all various flexibilities we have in mathematical morphology. I would skip, and I have another 5 minutes or 10 minutes. Professor Koo?
Sorry, Prof. Can you conclude?
I'll conclude very soon. Just 2-3 minutes. I'll just take.
Okay. Yeah.
And then, as I mentioned, John Bendixson's group, and what they have used is the morphological profiles and for the classification purpose. And this is for the DEMs, and so similarity regions, how to compute, and we have given a kind of how to compute the pairs, best pairs to worst pair, and through morphological distances. And then this is for some kind of landscape generations, and cartogram based work probably I would avoid. And so this is actually interpolation. And when you have a point data and how you convert that into a polygonal form, in many of GIS models, we require the data or the information to be in a contiguous form. But if you look at all these spots, these are all rain gauge stations. We have rainfall values at 34 rain gauge stations. But we want to show that in a kind of zonal map, and where we have used the morphological interpolations. And these are all the cartogram aspects. And I would skip this. I would skip this for spatial optimization. If you are asked which is the water body strategically located, and you want to create a kind of spatial policy, and there are so many water bodies, but you don't have money to protect all water bodies under drought condition. And if someone asks you which is the spatially and strategically important water body that we can protect, and we can have the morphological distances and find out some kind of spatial optimization theories. This is the morphological interpolations, and how you create a kind of all possible interpolations in between source and target, so that you can actually morphose it from source to target in a nice smooth transition. I would skip, and then with this, as I mentioned, I'll come back to the original statement. Mathematical morphology is an area of geoscience that most people don't realize will literally change the way they look at Earth. And mathematical morphology, a robust mathematical theory that needs attention by geoscience and remote sensing communities. And it is our duty to actually nurture the young minds to put them on track to think morphologically. I think this would really help many people to get attracted to mathematical morphology. And some of the published works and what we have done, and the remote sensing with mathematical morphology, which we edited in almost 10 years ago. And then if somebody is interested, filtering and segmentation with mathematical morphology, and this we have edited in 2012. And so very, very advancements they have put here. And then so about 3 years ago, IWGRS has asked, how do you showcase Indian remote sensing activities? And then they have given us a permission to publish papers. Mostly the first others are all Indians. That is the condition. Second, third, others can be any foreigner. But we released a special issue on Indian remote sensing and Earth observation. And if somebody is keen, and one can look at this particular book, which I have written in 2013, and the basics of morphology, and then their applications in geoscience, remote sensing, and GIS are given here. And the chapter 35 in this particular book and Handbook of Mathematical Geosciences is about a illustrative overview about mathematical morphology applied to geoscience and remote sensing. And then this is the call for papers, and probably I'll share it. And the deadline is there until 31st March next year. And it is about mathematical morphology in geoscience and remote sensing. And so which we are editing along with John Bendixson and Lorenzo Bruggione and Jocelyn Chonsett. And I would really circulate these things, and I have created an email, and very soon I'll send that. And then what is the use with all these algorithms developed to derive geometrical and topologically relevant information? Can we make use of this information gathered across time instances to better understand spatiotemporal behavior of phenomena and dynamical behavior of system-specific process? That would really give us many science outcomes. And we have to create a simple attractors, strange attractors, and how the behavioral patterns of the subsystems are different from the main systems. And we require, and we talk about big data, cyber physical systems, I would say that they are all of the same words with a different, disciplines we are talking. And then, so I will end with, at the end, this is not a job of one person. A great teamwork with excellent coordination is required to handle many open challenges when we are talking about geodynamical systems and extraterrestrial surfaces as the physical systems. So with this, I would like to thank you for giving me an opportunity. It's a great privilege. And so I have to list a long list of people to acknowledge, right from Professor Chua, and he has given what a wonderful freedom to me, and I always cherish, he's a great person. And then, as I mentioned, my most productive years are in Malaysia, and I always feel very nostalgic whenever I think about Malaysia. I feel like coming to Malaysia to spend at least a week. Thank you so much for all the Malaysian audience.
Thank you. Thank you, Prof. Dayasaga, once again for giving us a very comprehensive overview of the mathematical morphology. Sorry to rush you, Prof. Saga, because due to our tight schedule, we will definitely invite you again for another longer hour lecture. I know you can. Normally you deliver this for 2 hours, so we have to squeeze you into a half an hour.
No problem. This is a wonderful opportunity.
If I were to summarize, I think mathematical morphology, it changed the way we analyze remote sensing images and data, particularly in DM, the fractal geometry, how we actually understand our remote sensing data and the behavior. So I guess due to the time constraint, I have to end this session. For our audience, if you have any question to ask Prof. Dayasaga, you can still post your question, and later we can ask Prof. Saga to answer you. So I pass back this to our MC, Azmira. Thank you.
Thank you. Thank you very much.
Thanks, Prof. Dayasaga once again. Thank you. Yeah.
Thank you.
Thank you, Prof. Gu, and thank you also to Tuan Haji Azri Kamil and Professor Dr. B.S. Dayasaga for your enlightening keynotes. We definitely learned some new things today. So, dear audience member, a reminder that this workshop is based in Malaysia and all time are in GMT +8. It is now 10:30 a.m. So, ladies and gentlemen, we would like to announce that there is a Best Paper Award and Best Student Paper Award. Papers are evaluated based on the video presentation and paper contribution. Award winner will be announced during the closing ceremony today at 5:25 p.m. We shall start our first oral session at 10:30 after this. So this Zoom room will be open all day for all session. For session 3, we regret to inform you that presenter for paper 12 and The presenter for paper 11 and paper 12 could not attend today's workshop. So we greatly apologize for the inconvenience. Once again, welcome to the IEEE workshop on Geoscience and Remote Sensing 2020. That's all from me. Thank you.
So now we shall pass on to the next section, chaired by Associate Professor Dr. Chan.
Okay. A very good morning, ladies and gentlemen. I'm Chan Yikit from Multimedia University. So this is the session number 1 for the IEEE workshop. As mentioned by the MC, we will have the Best Paper Award and also Best Student Paper Award. So the paper will be evaluated based on the video and also the paper contribution. Right, okay. So we will start the session soon. So each of the paper will be presented by 10 minutes video and followed by 5 minutes Q&A session with the author, right? So please feel free to ask any question about the presentation using the Q&A tab at the bottom of the Zoom panel. So if you cannot access the Q&A tab, then you can also post the question in the chat box, all right? Okay. So without further ado, we will start the session number 1, paper number 1, okay, which is the invited paper from National Taipei University of Technology. This paper, the title of the paper is High Performance Computing Based Independent Data Structure using CUDA Refactoring for Flood Estimation, right? Let's welcome the presentation. Thank you.
Hello everyone. I'm going to present about our research topic titled High Performance Computing Based Independent Data Structure using CUDA Refactoring for Flood Estimation. The contents of my presentation are as follows: introduction, background, methodology, experimental results, and finally the conclusion. In recent days, the number of casualties caused by floods are rapidly increasing. In the year 2018 alone, the floods occurred in Japan has consumed about 225 lives, with further 13 people went missing. This has motivated us a lot to do the research related to the flood simulations and estimations. The major goal of this project is to compute the level of water flow that is estimated to be flooded even before the occurrence of floods in real time, and thus we can reduce the drastic effects caused by the floods. Our research was originally inspired by a computer package named SECHY21, which was proposed in the year 2002. This package used Fortran programming language. The computation time of this Fortran programming language is very slow compared to the real time. So, with the help of this package, we tried to enhance the performance of this flooding model by applying a parallel programming technique called CUDA, which I'll be explaining in the later slides. Research objectives. A module named iFlux was identified as the most computationally expensive module in the whole computer package. By using profiling, we have calculated all the time taken by each module, and finally we have calculated iFlux as the most computationally expensive module. A parallel programming technique called CUDA is applied to this iFlux module by refactoring its serial logic to parallel logic. Since CUDA is a parallel programming technique, we have modeled its logic to parallel. And on NVIDIA GeForce RTX 2080 Super GPU, it is shown that the iFlux module of our GPU CUDA model is 14 times faster than the original CPU model. Literature review. Our work is inspired by the previous research proposed by Dr. Shin, where the hydrodynamic model is used to solve 2D shallow water equations by using some interactive tools to provide triangular shaped grids which are unstructured, and the only problem of this research is that it exhibits data dependency problem. Since this was written in Fortran programming language, there is no problem called data dependency. Because we are going to convert this to CUDA, we have a problem of this data dependency, which I will be explaining in the later slides. In the other research, the authors implemented a finite volume method on unstructured meshes to solve shallow water equations. In one of the previous works, shallow water equations are parallelized utilizing CUDA technique using a state-of-art discretization method on explicit finite volume, where Cartesian grids and boundary conditions are used for faster simulations compared with physical scenarios. Coming to background, I'll try to explain what is CUDA and the architecture of CUDA. Compute Unified Device Architecture, in short called as CUDA. The advantages of CUDA are it enables parallel computing. We can code using CUDA-C as an extension. It is also called as parallel multi-core architecture. It solves computationally expensive problems or high-level computations. There are two main disadvantages of CUDA. One is, since it is developed by NVIDIA GPU cards, so it only works with NVIDIA GPU cards, and it is not suitable for low-level computations. You can see in the diagram the typical architecture of CUDA. Left side is the host side and the right side is the device side. Host side is normally CPU and the device side is normally GPU. CUDA kernel allocates size of the memory for the device code in CPU and it copies to GPU. And from the GPU, after the kernel is executed, the result from the device is copied back to the CPU and memory is released. This is the basic typical architecture of CUDA. Coming to the main architecture of CUDA, there are three main parts of CUDA. One is grids, second one is blocks, and the final one is threads. Grids contains blocks and blocks contains threads. And grids can make a call to CUDA from the host CPU. Grids in CUDA cannot be shared between two GPUs. A single GPU has 65,535 blocks. Blocks cannot be shared between two GPUs similar to grids. Whereas threads are the smallest parallel execution units. Threads in the same block share memory. They cannot change the data, but just communicate with the threads in different blocks. Each block contains 512 threads. Methodology. iFlux module. I was talking about iFlux module in my research objective, if you remember. Actually, after doing profiling, we have figured out that iFlux module is taking too much time. Like, it's computationally very expensive, so we thought to parallelize this iFlux module. There are many subroutines in the iFlux module. One is ROE1B, limiter, limiter 2, and limiter 2 HU. These three subroutines, limiter 2 HU, are not computationally expensive. Only ROE1B is computationally expensive. So we try to parallelize this ROE1B subroutine. As you see, these three subroutines, limiter, limiter 2, and limiter 2 HU, these are not high-level computations. These are very low-level computations as it doesn't take so much time to compute. So these are not suitable for parallel programming. Coming to unstructured mesh. Our dataset just looks like this. You can see inside, the edges inside the boundary are called internal edges and the edges at the boundary are called boundary edges. We have divided the terrain or the land using unstructured triangles or quadrilaterals. In our dataset, everything is a triangle, so let's consider triangle. The whole thing is called mesh. The unstructured triangles are called cells. You can see this is the unstructured mesh. The red triangle determines the cell. If you take this cell, it has 3 edges, E1, E2, E3. And if you take B, it's a quadrilateral cell and it has 4 edges. E1 is the common edge which is shared by both A and B. E4, E5, E6 are the remaining 3 edges of B. Original logic. If you see the original logic of ROE1B, it has two main for loops. One is to calculate the flux at internal edges and the other one is to calculate the flux at boundary edges. Flux is nothing but water flow. And if you consider this diagram, JL and JR are the left side and right side of the edge A. So as long as A is calculated, JL and JR are considered. Similarly, for A, B and C, as long as A, B and C are calculated, JL and JR of each edge, A, B and C are considered. This is called as data dependency and this logic is known as edge to cell mapping. Data dependency. Let me try to explain you what is data dependency. Consider two programming languages, serial programming and parallel programming. If there are two cores, namely A and B, consider C as the memory location, where the cores A and B reads and writes to the memory location C at the same time. From the perspective of parallel programming, two cores writing to the same location, there is a chance of conflict between the two cores, which in turn results in the error of the program. From the practical perspective, each core has a slight difference in physical characteristics and which results in the performance drop, and so the simultaneous writing to the location C cannot be achieved. The value stored in C might either be value of A or value of B. This dependency is known as data dependency. Output variables. The output variables for ROE1B subroutine are two. One is H flux and the other one is DU. DU represents delta and DU represents the physical quantities such as water depth, initial flow rate, and final flow rate. CUDA refactoring. Every application doesn't support parallelism. Some of the applications can support parallelism very easily, while the others do not show the ability to be parallelized. CUDA refactoring